Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The dawn of May 30th, 1832 broke over Paris, casting a somber light on a duel fought under circumstances frostery and intrigue. Évariste Galois, a young mathematician of barely 20 years, lay mortally wounded, the victim of a gunshot to the abdomen. He would succumb to his injuries the following day, his tragically short life extinguished, leaving behind a legacy of profound mathematical insight that would revolutionize the field of algebra. The circumstances surrounding Galois' death have been the subject of much speculation, ranging from romantic entanglements to political conspiracies. What remains certain is that his untimely demise robbed the world of a mind poised to make even greater contributions to mathematics. In his brief life, Galois had grappled with one of the most vexing problems of his time, determining when polynomial equations are solvable by radicals. This question, which had occupied some of the finest mathematical minds for centuries, found a definitive, albeit posthumous, answer in Galois' elegant and powerful theory. The quest to solve polynomial equations, expressions involving variables raised to various powers, dates back to antiquity. The Babylonians developed methods for solving quadratic equations. Those of the former x squared plus bx plus c equals 0. Later, mathematicians in India and the Islamic world made significant advances in understanding cubic and quartic equations, those involving powers up to the third and fourth degree respectively. The Italian mathematicians Scipione del Ferro, Niccolò Tartaglia, Gerolamo Cardano, and Lodovico Ferrari, working in the 16th century, famously discovered general formulas for solving these equations using radicals, that is, expressions involving square roots, cube roots, and higher-order roots. However, a fundamental question remained unanswered. Could a similar formula be found for polynomial equations of degree 5 or higher, the so-called quintic and higher degree equations? For centuries, mathematicians sought such a general solution, but all efforts proved fruitless. It was not until the early 19th century that Paolo Ruffini and Niels Henrik Abel independently proved that there exists no general algebraic formula for solving quintic equations. This result, while groundbreaking, did not provide a complete answer. It established the impossibility of a universal formula, yet it left open the possibility that some specific quintic equations might still be solvable by radicals. This is where Galois' genius shone. He went beyond simply demonstrating the insolvability of the general quintic. He developed a comprehensive theory that provided a criterion for determining precisely which polynomial equations, regardless of their degree, are solvable by radicals. His approach was revolutionary, introducing the concept of a group associated with each polynomial equation. This group, now known as the Galois group, encapsulates the symmetries of the roots of the equation and provides a powerful tool for analyzing its solvability. Central to his theory is the insight that a polynomial equation is solvable by radicals if and only if its Galois group possesses a specific structure, namely, that it is a solvable group. Galois' theory, known as Galois theory, represents a profound shift in mathematical perspective. It moves away from the specific coefficients of a polynomial equation and focuses instead on the abstract algebraic structure of its roots. This approach not only solved the long-standing problem of solvability by radicals, but also laid the foundation for modern group theory, a branch of mathematics that has found applications in diverse fields, including physics, chemistry, and computer science. The story of Évariste Galois is one of both brilliance and tragedy. His life was marked by political turmoil, academic setbacks, and ultimately, a premature death. His mathematical ideas, initially rejected and misunderstood, were only fully appreciated after his passing. Today, Galois' theory stands as a testament to his extraordinary genius, a cornerstone of modern algebra, and a powerful tool for understanding the fundamental nature of mathematical structures. This essay will explore the life and work of Évariste Galois, tracing his intellectual journey from his early mathematical explorations to his groundbreaking theory of solvability by radicals. It will delve into the mathematical concepts underlying Galois' theory, providing a clear and accessible explanation of his group-theoretic approach to polynomial equations. Furthermore, it will examine the historical context in which Galois developed his ideas, highlighting the challenges he faced in gaining recognition for his work. It will also discuss the profound impact of Galois' theory on the development of modern mathematics, illustrating its enduring relevance and its connections to other areas of science and technology. We will begin by examining Galois' early life and education, exploring the factors that shaped his mathematical development and the obstacles he encountered in his pursuit of knowledge. We will then turn to a detailed analysis of his mathematical contributions, focusing on his theory of solvability by radicals and the underlying concepts of group theory. We will explain how Galois associated a group with each polynomial equation and how the structure of this group determines the equation's solvability. Following this, we will delve into the reception of Galois' work by the mathematical community, examining the reasons for its initial rejection and the subsequent recognition of its significance. We will explore the roles played by prominent mathematicians such as Cauchy, Poisson, and Liouville in the dissemination and validation of Galois' ideas. Finally, we will discuss the lasting impact of Galois theory on modern mathematics, highlighting its connections to other areas of algebra, number theory, and geometry. We will also explore its applications in other fields, such as physics and computer science, demonstrating the far-reaching consequences of Galois' revolutionary insights. Through this exploration, we aim to provide a comprehensive understanding of Évariste Galois' life, work, and enduring legacy, celebrating his contributions to mathematics and honoring his memory as one of the most brilliant and tragic figures in the history of science. Évariste Galois' journey into the realm of mathematics began in Bourg-Lorraine, a commune near Paris, on October 25, 1811. His parents, Nicolas Gabriel Galois and Adélaïde Marie de Montet, provided him with an initial education steeped in classical literature and rigorous thought. His mother, the daughter of a jurist, possessed a formidable intellect and served as Évariste's primary educator until he was 12. She instilled in him a strong foundation in Latin and Greek, as well as a skepticism towards authority that would later characterize his approach to mathematics and politics. This early homeschooling proved formative, shaping Galois' intellectual independence and fostering a deep appreciation for logic and reasoning. He absorbed the classics, engaging with the works of the great thinkers of antiquity, developing a mind that valued precision and clarity. This foundation would later serve him well as he grappled with the complexities of abstract algebra. In 1823, at the age of 12, Galois entered the Lycée Louis le Grand, a prestigious Parisian secondary school. Initially, he excelled, demonstrating a natural aptitude for rhetoric and composition. However, the rigid structure and traditional curriculum of the lycée soon began to stifle his intellectual curiosity. To describe a specific physical situation, the cooling of a particular iron ring, for instance, the equation requires flesh and blood. This is provided by what are known as initial and boundary conditions. The initial condition specifies the state of the entire system at the starting moment, time t equals 0. It is a snapshot of the temperature distribution throughout the whole object. One might imagine, for example, a long metal bar heated in the middle by a flame and then left to cool. The initial condition would be a function describing this high temperature in the center, tapering off towards the ends. The boundary conditions describe how the object interacts with its environment at its surfaces for all subsequent time. Fourier considered several possibilities. The boundary could be held at a fixed temperature, for example, if the ends of our metal bar were plunged into ice water baths. This is now known as a Dirichlet boundary condition. Alternatively, the boundary could be perfectly insulated, meaning no heat can escape. Mathematically, this translates to the condition that the temperature gradient perpendicular to the surface must be 0. This is a Neumann boundary condition. A third, more realistic case involves the boundary losing heat to the surrounding air, a process governed by Newton's law of cooling, where the rate of heat loss is proportional to the temperature difference between the surface and the ambient air. This is a Robin boundary condition. The formulation of the problem was now complete. Fourier had constructed a complete mathematical framework, a governing partial differential equation, coupled with a specific initial temperature distribution and a set of boundary conditions defining the object's interaction with the world. He had transformed a messy qualitative physical problem into a precise, well-posed mathematical one. The equation itself was a triumph of physical modeling, a testament to the power of calculus to describe the continuous processes of nature. It established the grammar for an entire new field of mathematical physics. The monumental intellectual edifice was framed. The task that lay ahead, the task that would occupy him for years and provoke a revolution in mathematics, was to find the key to unlock its solutions. With the physical problem elegantly captured in the language of differential equations, the central intellectual hurdle remained. How could one discover a function, a specific mathematical expression for temperature, that would satisfy the heat equation at every point in space and for every moment in time, while simultaneously matching an arbitrary and potentially quite irregular initial temperature distribution? Cauchy, known for his contributions to analysis and number theory, had been appointed to review Galois' work but apparently misplaced it, a devastating blow to the young mathematician's aspirations. Undeterred, Galois submitted a second paper to the Académie des Sciences, this time addressing it to Simeon Denis Poisson, a renowned physicist and mathematician. Poisson examined the paper but deemed it incomprehensible, suggesting that it needed further development. He encouraged Galois to revise and resubmit his work, but the mathematician's untimely death prevented him from doing so. The failure to gain recognition from Carson and Poisson was a source of deep frustration for Galois. He felt that his work was not being taken seriously by the mathematical establishment, and he struggled to find a receptive audience for his revolutionary ideas. The loss of his first paper and the rejection of his second contributed to a growing sense of isolation and disillusionment. The socio-political climate of post-Napoleonic France further complicated Galois's intellectual development. The Bourbon Restoration had brought a period of political reaction, with the monarchy seeking to suppress dissent and maintain its authority. Galois, who held Republican sympathies, found himself increasingly at odds with the conservative political order. He became involved in radical political movements, participating in demonstrations and expressing his opposition to the monarchy. His political activism led to several arrests and imprisonments, further disrupting his mathematical pursuits and contributing to his sense of alienation. The turbulent political environment created a climate of uncertainty and instability, making it difficult for Galois to focus on his research. The July Revolution of 1830, which overthrew the Bourbon monarchy and replaced it with the July monarchy under Louis-Philippe, initially raised hopes for a more liberal political order. However, the new regime proved to be only marginally more tolerant than its predecessor, and Galois continued to face persecution for his political activities. In December 1830, Galois was arrested for making a toast to King Louis-Philippe with a dagger in his hand. Although he claimed that the toast was actually a threat against the king, he was imprisoned for several months. During his imprisonment, he continued to work on mathematics, further developing his ideas on the theory of equations. Upon his release from prison in April 1832, Galois found himself embroiled in a personal conflict that would ultimately lead to his tragic death. He became involved in a duel, the circumstances of which remain shrouded in mystery. Some accounts suggest that the duel was provoked by a political rival, while others claim that it was the result of a romantic entanglement. Regardless of the precise circumstances, the duel proved fatal for Galois. On the eve of the duel, he spent the night writing a letter to his friend Auguste Chevalier, outlining his mathematical discoveries and imploring him to preserve his work for posterity. This letter, now known as Galois' Mathematical Testament, contains a concise summary of his groundbreaking contributions to the theory of equations. The following day, May 30th, 1832, Galois faced his opponent in a duel. He was mortally wounded and died the next day at the age of 20. His untimely death cut short a brilliant mathematical career, leaving behind a legacy of revolutionary ideas that would transform the field of algebra. The loss of such a promising talent was a tragedy for mathematics, depriving the world of the further contributions that Galois might have made. The tragic death of Évariste Galois at such a young age underscores the profound loss to the mathematical community. The letter he penned to Auguste Chevalier on the eve of his duel serves as a poignant reminder of his genius and a roadmap to the revolutionary ideas he had conceived. This mathematical testament hinted at solutions to problems that had vexed mathematicians for centuries, setting the stage for a new era in algebra. Central to Galois' work was the problem of solvability by radicals. This question, which had occupied some of the greatest mathematical minds, concerns finding a general formula, akin to the quadratic formula, that can express the roots of any polynomial equation in terms of its coefficients, using only the operations of addition, subtraction, multiplication, division, and the extraction of roots, also known as radicals. Let's consider the historical context. The quest for such formulas stretches back to antiquity. The solution to the quadratic equation, that is, a polynomial equation of degree 2, was known to ancient civilizations, including the Babylonians and the Greeks. The familiar quadratic formula, which expresses the roots of the equation x squared plus bx plus c equals 0, as x equals negative, b plus or minus. The square root of b squared minus 4ac, all divided by 2a, provides an explicit method for finding the roots of any quadratic equation, given its coefficients a, b, and c. The story continues with cubic equations, those of degree 3. In the 16th century, Italian mathematicians Scipione del Ferro, Niccolò Tartaglia, and Gerolamo Cardano made significant breakthroughs. Cardano, in his seminal work Ars Magna, published in 1545, presented a general method for solving cubic equations. This solution, often referred to as Cardano's formula, expresses the roots of a cubic equation in terms of radicals involving its coefficients. The formula, while complex, demonstrates that a general solution for cubic equations using radicals does indeed exist. Shortly after the resolution of the cubic came the resolution of the quartic, or degree 4, polynomial. Also within Cardano's Ars Magna, his student, Ludovico Ferrari, published a general solution for equations of degree 4. The solution, while considerably more intricate than that for cubics, once again demonstrates the existence of an algebraic solution expressing the roots in terms of radicals. For centuries, mathematicians sought a similar general solution for quintic equations, those of degree 5, and higher degree polynomials. The pursuit was intense, with many believing that a formula analogous to those for quadratic, cubic, and quartic equations must exist. Eminent mathematicians devoted considerable effort to finding this elusive quintic formula. However, these efforts proved fruitless. The lack of success in finding a general solution for the quintic equation led some to suspect that such a solution might not exist. This suspicion was ultimately confirmed in the late 18th and early 19th centuries, marking a pivotal moment in the history of algebra. Paolo Ruffini, an Italian mathematician, made the first attempt to prove the impossibility of solving the general quintic equation by radicals. His proof, published in 1799, contained gaps and was not fully accepted by the mathematical community. Niels Henrik Abel, a Norwegian mathematician, provided the first complete and correct proof of the impossibility of solving the general quintic equation by radicals. Abel's proof, published in 1824, demonstrated definitively that there is no general formula involving only algebraic operations and radicals that can express the roots of all quintic equations in terms of their coefficients. This groundbreaking result, now known as the Abel-Ruffini theorem, shattered the long-held belief that such a formula must exist and marked a fundamental shift in the understanding of polynomial equations. The Abel-Ruffini theorem, therefore, established a limit to the solvability of polynomial equations by radicals. It showed that while equations of degree 4 or less always have solutions expressible in terms of radicals, this is no longer the case for equations of degree 5 or higher. The theorem leaves open a crucial question. While a general formula for quintics is impossible, are there specific quintic equations or higher degree equations that can be solved by radicals? The Abel-Ruffini theorem only says that a general solution is impossible, not that all such equations are unsolvable by radicals. This is where Galois' profound contribution enters the picture. Galois sought to determine precisely which polynomial equations are solvable by radicals. He developed a comprehensive theory that provides a criterion for determining whether a given polynomial equation can be solved using only algebraic operations and radicals. His work went far beyond the Abel-Ruffini theorem, which merely stated the impossibility of a general solution for quintics. Galois provided a method for analyzing any given polynomial equation to determine whether it is solvable by radicals. Galois' theory provides a complete and elegant solution to the problem of solvability by radicals. It not only explains why the general quintic equation cannot be solved by radicals, but also provides a way to determine which specific polynomial equations, regardless of their degree, can be solved in this way. The implications of Galois' work are far-reaching, extending beyond the theory of equations to other areas of mathematics, including group theory and field theory. His ideas laid the foundation for modern algebra and continue to inspire mathematicians today. The central question that Galois addressed, therefore, was not simply whether a general formula existed, as Abel and Ruffini had shown it did not, but rather under what conditions any given polynomial equation could be solved by radicals. It is to the unveiling of his solution that this narrative now turns. Galois embarked on a radical reframing of the problem. His approach transcended the direct search for solutions to polynomial equations, instead focusing on the relationships between the roots themselves. He recognized that the symmetries inherent in these relationships held the key to unlocking the secrets of solvability. To understand Galois' revolutionary idea, it is necessary to introduce the concept of a group, though not in its full abstract generality, but rather in the specific context of permutations of roots. Imagine a polynomial equation. It possesses a certain number of roots, which may be real or complex. Galois considered the set of all possible ways to rearrange or permute these roots. A permutation in this context is simply a rearrangement of the roots. For example, if a polynomial has three roots, labeled as root 1, root 2, and root 3, one possible permutation would be to swap root 1 and root 2, leaving root 3 unchanged. Another permutation might cycle the roots, sending root 1 to the position of root 2 to the position of root 3, and root 3 to the position of root 1. These permutations are not arbitrary. Galois focused on those permutations that preserve algebraic relationships between the roots. An algebraic relationship is an equation involving the roots and rational numbers, such as root 1 plus root 2 equals 3 times root 3. If a permutation preserves an algebraic relationship, it means that after applying the permutation to the roots in the equation remains true. The set of all such permutations, those that preserve algebraic relationships between the roots, forms a group in the mathematical sense. A group is a set of elements together with an operation that satisfies certain properties: closure, associativity, identity, and invertibility. In this case, the elements are the permutations, and the operation is composition, which means applying one permutation after another. Closure means that if you compose two permutations in the group, the result is also a permutation in the group. Associativity means that the order in which you compose three or more permutations does not matter. The identity element is the permutation that leaves all the roots unchanged. And invertibility means that for every permutation in the group, there is another permutation in the group that undoes it. This group, associated with a polynomial equation, is called the Galois group of the equation. It encapsulates the symmetries of the roots and their algebraic relationships. The size of the Galois group, the number of permutations it contains, reflects the complexity of these relationships. A small Galois group indicates a high degree of symmetry and a simpler structure, while a large Galois group suggests a more intricate and less symmetrical arrangement of roots. Galois' genius lay in recognizing that the solvability of a polynomial equation by radicals is intimately connected to the structure of its Galois group. He discovered that a polynomial equation is solvable by radicals if and only if its Galois group is solvable in a specific technical sense. To understand what it means for a group to be solvable, one must delve into the concept of a composition series. A composition series of a group is a sequence of subgroups, starting with the group itself and ending with the trivial group, consisting only of the identity element, such that each subgroup in the sequence is a normal subgroup of the previous one, and the quotient groups between successive subgroups are simple. A normal subgroup is a subgroup that is invariant under conjugation, meaning that conjugating any element of the subgroup by any element of the group results in another element of the subgroup. A simple group is a group that has no non-trivial normal subgroups. A group is considered solvable if it possesses a composition series in which all the quotient groups are cyclic, meaning that they are generated by a single element. In other words, a solvable group can be broken down into a series of simpler and simpler subgroups, each of which is a normal subgroup of the previous one, until one arrives at the trivial group, and each step in this breakdown involves a cyclic quotient group. Galois' central theorem, therefore, establishes a direct link between the algebraic problem of solving polynomial equations by radicals and the group-theoretic property of solvability. It states that a polynomial equation is solvable by radicals if and only if its Galois group is a solvable group. This theorem provides a precise criterion for determining whether a given polynomial equation can be solved using radicals. The beauty of Galois' theory resides in its ability to transform a seemingly intractable algebraic problem into a problem of group theory. Instead of grappling with the intricacies of polynomial equations directly, one can instead analyze the structure of their associated Galois groups. If the Galois group is solvable, then the equation is solvable by radicals, otherwise it is not. This criterion immediately explains why the general quintic equation is not solvable by radicals. The Galois group of the general quintic equation is the symmetric group on 5 elements, which is the group of all possible permutations of 5 objects. This group is not solvable, as it contains a simple, non-cyclic subgroup, the alternating group on 5 elements. Therefore, according to Galois' theorem, the general quintic equation cannot be solved by radicals. Furthermore, Galois' theory provides a method for determining which specific polynomial equations are solvable by radicals. Given a particular polynomial equation, one can, in principle, determine its Galois group and then analyze its structure to see if it is solvable. If it is, then the equation is solvable by radicals, and Galois' theory provides a roadmap, albeit a complex one, for finding the solution. It is important to emphasize that Galois' theory does not provide a general formula for solving solvable polynomial equations. Rather, it provides a criterion for determining whether a solution exists in terms of radicals. Finding the actual solution, even when it is known to exist, can still be a challenging problem. Galois' theory represented a profound shift in perspective. It moved away from the direct pursuit of formulas and towards a structural understanding of the relationships between the roots of polynomial equations. This shift not only solved the long-standing problem of solvability by radicals, but also laid the foundations for modern algebra, with its emphasis on abstract structures and their properties. Galois' work demonstrated the power of symmetry in solving mathematical problems and opened up new avenues of research that continue to be explored today. His untimely death at the age of 20 illustrates a tragic irony, as his revolutionary ideas were initially met with indifference and misunderstanding, only to later become cornerstones of modern mathematics. The true significance of Galois' profound contributions, however, was not immediately recognized. His initial submissions to the Académie des Sciences were either lost or misunderstood, and the mathematical community at the time seemed ill-equipped to grasp the revolutionary nature of his ideas. The prevailing mathematical landscape, still deeply rooted in classical approaches, struggled to accommodate Galois' abstract and structurally oriented perspective. His work remained largely unknown for many years, a testament to the challenges faced by groundbreaking ideas that arrived before their time. It was only through the persistent efforts of Joseph Liouville that Galois' genius eventually came to light. Liouville, a prominent mathematician in his own right, recognized the immense value of Galois' manuscripts after reviewing them several years after Galois' death. In 1843, Liouville announced to the Académie that he had found in Galois' papers a solution, in his opinion, as correct as it was profound, to the problem of whether or not an equation could be solved by radicals. However, it wasn't until 1846, 14 years after Galois' death, that Liouville finally published Galois' manuscripts in the Journal de Mathématiques Pures et Appliquées. This publication marked a turning point, as it made Galois' work accessible to a wider audience and paved the way for its eventual acceptance and development. Liouville's publication served as a catalyst, sparking interest and inspiring further research in the directions Galois had pioneered. Mathematicians began to grapple with the abstract concepts and structural insights that formed the core of Galois' theory. The initial response was cautious, with many mathematicians struggling to fully comprehend the depth and originality of Galois' ideas. Nevertheless, a slow but steady process of assimilation and refinement began, gradually transforming Galois' groundbreaking work into a cornerstone of modern algebra. Following Liouville's publication, mathematicians such as Richard Dedekind and Leopold Kronecker played pivotal roles in further developing and generalizing Galois theory. Dedekind, known for his work on algebraic number theory and the rigorous formulation of real numbers, brought his characteristic clarity and precision to the study of Galois' ideas. He meticulously examined Galois' manuscripts, clarifying obscure points and providing more accessible presentations of the key concepts. Dedekind's work helped to solidify the foundations of Galois theory and make it more readily understandable to a broader mathematical audience. Kronecker, another influential figure in algebra and number theory, also made significant contributions to the development of Galois theory. He emphasized the importance of working within a well-defined algebraic framework and sought to simplify and generalize Galois' results. Kronecker's work on field extensions and the theory of algebraic numbers provided a fertile ground for the further exploration of Galois' ideas. He also contributed to the development of the concept of the Galois group, which plays a central role in the theory. Kronecker's famous quote, "God made the integers, all else is the work of man," reflects his deep commitment to the foundations of mathematics and his belief in the importance of rigorous algebraic reasoning. A more abstract and axiomatic approach to Galois theory emerged in the 20th century, largely due to the work of Émile Artin. Artin, a highly respected mathematician known for his contributions to algebra, number theory, and analysis, provided a streamlined and elegant presentation of Galois theory that emphasized the role of field extensions and their automorphism groups. His approach, which built upon the earlier work of Dedekind and Kronecker, made Galois theory more accessible and applicable to a wider range of problems. Artin's lectures on Galois theory became highly influential, shaping the way the subject is taught and understood to this day. His emphasis on clarity and abstraction helped to solidify Galois theory's place as a central pillar of modern algebra. The impact of Galois theory on mathematics has been profound and far-reaching. It revolutionized algebra by shifting the focus from solving equations to understanding the underlying structures and symmetries that govern their solutions. Galois's work introduced the concept of a group as a fundamental algebraic object, paving the way for the development of group theory as a major branch of mathematics. Group theory, in turn, has found applications in diverse areas such as physics, chemistry, and computer science. Furthermore, Galois theory has had a transformative impact on number theory. It provides a powerful framework for studying the properties of algebraic numbers and their relationships to polynomial equations. The theory has been instrumental in solving long-standing problems in number theory, such as the determination of which integers can be expressed as the sum of two squares. Galois theory continues to be an active area of research in number theory, with ongoing efforts to generalize and extend its results. Galois's ideas have also found unexpected applications in other areas of mathematics and science. In geometry, Galois theory provides insights into the symmetries of geometric objects and the construction of geometric figures. In physics, group theory, which originated from Galois's work, plays a crucial role in understanding the fundamental symmetries of the universe. From the classification of elementary particles to the study of crystal structures, group theory provides a powerful tool for analyzing and understanding physical phenomena. The enduring legacy of Galois's work is a testament to the power of abstract mathematical thought and its ability to solve long-standing problems and shape our understanding of the world. Galois's theoretical framework extends far beyond the specific problem of polynomial equations, offering a profound lens through which to examine solvability across diverse mathematical and scientific domains. The core concept of relating field extensions to groups of automorphisms, the essence of Galois theory, provides the necessary foundation for understanding when solutions to equations can be expressed through radicals, not only in algebra but in various related fields. Consider, for instance, the realm of differential equations. While Galois theory directly addresses polynomial equations, the analogous theory for differential equations, known as differential Galois theory, builds upon Galois's initial insights. Differential Galois theory examines the symmetries of solutions to differential equations. It determines when solutions can be expressed in terms of elementary functions, extending the notion of solvability by radicals to a new class of equations. This extension is crucial in many areas of physics and engineering, where differential equations are used to model a wide variety of phenomena, from the motion of objects to the flow of heat. The influence of Galois's work is also felt strongly in cryptography. Modern cryptographic systems rely heavily on the difficulty of solving certain mathematical problems, such as factoring large numbers or computing discrete logarithms. The algebraic structures underlying these problems can be analyzed using the tools of Galois theory. Understanding the symmetries and automorphisms of these structures helps cryptographers design more secure systems. Furthermore, the finite fields that play a central role in Galois theory are also essential in the construction of error-correcting codes, which are used to ensure the reliable transmission of data over noisy channels. These codes rely on the properties of polynomials over finite fields, and Galois theory provides a deep understanding of these properties. Coding theory in general benefits significantly from the application of Galois theory. Error-correcting codes, essential for reliable data transmission and storage, are often constructed using algebraic structures based on finite fields. Galois theory provides the theoretical underpinnings for understanding the properties of these codes, including their error-correcting capabilities and their efficiency. By analyzing the symmetries and automorphisms of the underlying algebraic structures, coding theorists can design codes that are more robust and efficient. The use of Galois theory in coding theory is a testament to the practical relevance of abstract mathematical concepts. The study of symmetries, so central to Galois's work, has become a cornerstone of modern physics. Group theory, which emerged from Galois's investigation into the solvability of polynomial equations, provides a powerful framework for understanding the fundamental laws of nature. In particle physics, The Standard Model, which describes the fundamental particles and forces of the universe, is based on the symmetries of space-time and internal symmetries related to the fundamental forces. Group theory is used to classify elementary particles according to their properties and to predict the interactions between them. The symmetries of space-time, such as rotational and translational invariance, lead to conservation laws, such as the conservation of energy and momentum. These conservation laws are fundamental to our understanding of the physical world. Condensed matter physics also relies heavily on group theory to understand the properties of materials. The symmetries of crystal lattices determine the electronic and vibrational properties of solids. Group theory is used to classify the possible crystal structures and to predict the behavior of electrons and phonons in these structures. This understanding is crucial for designing new materials with desired properties, such as high-temperature superconductors or materials with novel electronic properties. The application of group theory and condensed matter physics is a prime example of how abstract mathematical concepts can have profound implications for technological advancements. The enduring power of Galois' ideas lies in their ability to connect seemingly disparate areas of mathematics and science. His work provides a unifying framework for understanding the concept of solvability, whether it be the solvability of polynomial equations, differential equations, or the problems encountered in cryptography and coding theory. The symmetries that he uncovered in the solutions to algebraic equations have become a guiding principle in modern physics, shaping our understanding of the fundamental laws of nature. The impact of Galois' work is far-reaching and continues to grow as mathematicians and scientists find new applications for his ideas. Évariste Galois' life, tragically cut short at the age of 20, stands as a poignant reminder of the profound contributions that can emerge from even the briefest of existences. His untimely death, shrouded in circumstances that speak of youthful impetuosity and political turmoil, robbed the world of a mathematical genius whose potential was only beginning to unfold. The night before his duel, he feverishly documented his mathematical insights, entrusting them to posterity with a sense of urgency that underscores the magnitude of his discoveries. This act, a race against time, encapsulates the dedication and passion that drove his intellectual pursuits. Despite the brevity of his life, Galois left an indelible mark on the landscape of mathematics. His theory, initially met with skepticism and incomprehension, has since become a cornerstone of modern algebra and a powerful tool in diverse fields. Galois' work exemplifies the enduring power of abstract mathematical thought. It demonstrates how seemingly esoteric concepts can provide solutions to long-standing problems and unexpectedly shape the technologies that define our modern world. The abstract structures he investigated, the symmetries he unveiled, and the connections he forged continue to resonate with mathematicians and scientists today. The story of Évariste Galois serves as an inspiration to those who pursue knowledge and innovation. It underscores the importance of perseverance, the value of abstract thought, and the enduring legacy that can be created through intellectual curiosity and rigorous inquiry. His contributions, born from a mind of exceptional brilliance and nurtured in an environment of political and social upheaval, stand as a testament to the human capacity for creativity and the transformative power of mathematical ideas. Galois' legacy lives on, not only in the theorems and theories that bear his name, but also in the countless applications of his work that continue to shape our understanding of the world and improve our lives. The echoes of his mathematical genius continue to reverberate through the corridors of science and technology, a lasting tribute to a young man whose life, though tragically brief, left an enduring imprint on the fabric of human knowledge.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.